Now we're gonna study the torque on a current loop. Let's pick up some loop. For example, here is a rectangular loop. We call this distance B, this distance A, and then we have a current I, okay, going through the wire. So we have, here's the current I. And then we have a magnetic field pointing onto the paper. So here is the B field. This is the B field. So this B field here is an outside B field. It doesn't belong to this loop. The loop has its own B field, but this B field here is an outside. It could be coming from a magnet or from some other loop, okay? Now, we need to know the forces that are acting on these sections of the loop. Let's look at the right section here, this section here. Now, I have to use the right hand rule. Now the problem is I'm sitting this way, so my fingers, so what I'm gonna do, I'm gonna rotate the paper, okay, so make it easy for me. So I go like this. I'm looking at this section here, this one. So I go like that. And then, now, here is the current, is going down. Look at the B field going into the paper. So I go down, the paper, towards the paper. Look at my thumb, it's going to the left. So the force is going to the left. So now, the force is going to the right. Because remember, I rotated the paper. Now let's look at the force acting on the top section. Top section, I go like this, you see? The current is going to the right, so my fingers are going to the right. And then I rotate my fingers towards the B field. The B field is going into the paper. And look at my thumb is going up. So the force is going up like that. Let's look at the left side. Remember, the B field is going onto the paper. This is an outside B field. And look at the current is going up. So my fingers will go with the current. The palm of my hand is pointing towards the B field in the direction of the B field. And look, as I rotate my finger, look what happened to my thumb. My thumb is pointing to the left. So I have here. Now, if you look at the bottom section, the current is going to the left. My fingers follow the current. And then the B field is going down. The palm of my hand needs to be pointing in the direction of the B field. So I rotate my finger. Look at my thumb. It's going down. So the force is going down. So what this magnetic field is doing is trying to stretch the loop, pulling from each section. Now what we're going to do, we're going to rotate. We're going to flip this loop. Flip this loop and we make it, you see this section here? This section? We're going to turn it like that. This is the B section. You see this section here? You cannot see it's behind there. So what I did to the loop is I went like this. It's very hard to, I went like that. You see? Like that. You cannot see the other section of the loop. You see only, see, I went like that. Now, I see only this section. Now, this force here is this one. This force here is this one. This length here is B. Now we go at the center of B, we draw a line there. I have an angle here, I call it theta. Okay, I have the perpendicular here. This is, I also call it theta. This one is theta. Now, this one here is perpendicular, like that. Now, what we need to do, we need to calculate the torque. So the torque, I put here, torque is equal to R cross F. Okay? Now, this torque, which is R cross F, we can change it to magnitude. We put torque is equal to RF sine theta. And theta will be the angle between F and R. You can see this is R. We take this to be our origin. This is R and that's F. And the angle between them is this theta there. Now, we found the torque. Now, this R here is this distance. I can call it B. So I put torque is equal to B F sine theta. R is B. Now what I do, I look at that. There is a wire. This wire you see here, this wire is there, is going into the paper, and it's there. So it's like that. And the force is pointing up. And this wire here, this section, which is A, is actually, the wire is going like that, like the pen, there. Now this force is acting on this wire here. It's acting on that wire. And we know the force F is equal to I, the current, times the length A and B. You see the force is going up like that, and the B field, if you look at the force is up, the B field is down, going like that. They are perpendicular. The force is going north, and this one is going down, so they're perpendicular. So I don't have sine theta. So this is F, acting on that wire. Now we take this F and plug it there. So the torque is equal to B, I, A, and B, and then I have sine theta. So this is the torque that's acting on this loop here. Now, we have only one loop. If we have many loops, the torque will be, torque is equal to the number of loops. And I put here I. You see this BA is B times A is the area. So I put here A. And then I put B and I put sine theta. And this A is the area of the loop. And A is equal to A times B. That's why I took this A times B and make it A. Okay? Now, if we go back to one loop, if we have one loop, I can put torque is equal to I, A, B, sine theta. This is for one loop. This is for one loop. I'm sorry. For one loop. Torque is equal to I, A, B, sine theta. Now, this A is the area of rectangle. What happens if we have a circle? If we have a circle, this A will be pi r squared. So I put here r, if we have a circle. And now, we're going to have the torque is equal to I pi r squared B sine theta. pi r square b sine theta. Now what's so interesting, this pi r square I, this one here, is called the magnetic moment. They call it mu. This mu is equal to area times the current. Now, our equation will look like this. We have mu b sine theta. So this is the torque. Mu, and mu is A times I. A is the area of the loop, and I is the current on the loop. So now I come back here where we have space in this section here, and then I put torque is equal to mu b sine theta. Now the torque can be a vector, so I change to a vector, and I put here mu cross b. So the torque is equal to the magnetic moment cross the B field. Now, when we did electricity, we studied the charges. The torque, okay, is equal to the dipole moment cross the electric field. So there is some similarity. Look at here, we have electric field, here we have magnetic field. This is the magnetic moment, this is the dipole moment. So there is some parallelism. So this is the torque that acts on this loop. So if you put some current in a loop and you put that loop in a magnetic field, then the loop will rotate, will try to rotate, because there is a force acting on this top section. You see, when this one pulls down, this one pulls up, this guy is going to try to rotate like that. See, because pushing down. Let's see if the wire section was like this. This one pushing up, pushing. Let me make it going up like this. This one coming down like that. F. So this thing is gonna try to spin. So this is the physics of a motor, electric motor. So the electric motor works like this. That's why you see so many wires. The motor is heavy. Electric motor is heavy because you have so many wires, because they want to increase N. Because if N is so big, the torque is so big, so you can pull or you can rotate. The thing will have strong rotation. If you connect it to a belt or something, it will make that belt turn. So that's why you have to have many loops. If you look at your fan in your house, look inside, you're gonna find so many loops of wire, copper wire turning, because they need to increase the torque. Okay, have a good day. Bye.